Welcome to this explainer. Okay, have you ever actually stopped to think about how computers, which are fundamentally just, arrangements of silicon processing electrical currents, actually make complex decisions? Well, it all boils down to a set of absolute gatekeepers. Today we are unpacking the real foundation of computing, logical expressions.
Okay, let's dive into this. We're going to take a building blocks approach today. We'll start by meeting logical expressions generally. Look at the and or operators, check out the not operator, and then we'll actually trace some real code with an or example, and finally an and not example.
Section 1. Meet logical expressions. We are looking at the absolute atomic units of computer logic here. Think about all the incredibly complex things computers do, right? Rendering stunning 3D graphics, routing global internet traffic, or just recommending your next favorite song. Out of all of that mind-boggling complexity, the core logic literally comes down to just three basic operators, and, or, and not. Whenever a computer program reaches a fork in the road, it uses these exact operators to determine which path to take. Moving right along to Section 2, the and or operators. Let's see exactly how these gatekeepers make decisions. What's really interesting about this slide is the absolute strictness of the and operator. It requires perfection. If the first value is true and the second value is true, the result is true. But notice what happens the moment any false enters the mix. True and false, that's false. False and true, false. False and false, still false. With an and operator, every single condition must be met. No exceptions. Now contrast that with the or truth table. This one is way more flexible. If just one value is true, the whole result is true. True and true, true. True and false, still true. False and true, true. The only time the OR operator evaluates to false is if absolutely everything is false. False and false gives us false.
So, just to summarize the difference, the AND operator is your strict gatekeeper, requiring everything to be perfectly true. The OR operator is the flexible one. It lets you pass as long as at least any one thing is true. Keep that contrast in your head, because it completely changes how a program behaves.
Section 3. The not operator. This one acts a little differently than the first two. You can just think of the not operator as the flipper. It's incredibly punchy. Whatever value you give it, it literally just gives you the exact opposite back. So true becomes false and false becomes true. It's kind of the ultimate contrarian of the computer logic world.
Section 4, Logic in Action, an OR example. It is time to stack our building blocks and see how these rules govern actual pseudocode.
So the crucial point is how the code uses the OR operator right at the top as a gatekeeper to decide whether to run x equals x plus 1 or y equals y plus 1. It's asking the system, is x equal to y or is x less than y? Let's test this. What happens when x is 4 and y is 2? Try to apply that OR truth table we just learned in your head for a second before we reveal the answer.
Okay, let's walk through the evaluation step by step, exactly how a computer would do it. Step 1. Does 4 equal 2? Nope, that's false. Step 2. Is 4 less than 2? No, also false. Step 3. We apply the OR operator. We have false or false. And as we know, that's the one scenario that results in false. So taking a look at the isolated trace table result, because the whole statement was false, the code totally bypassed the if block and dropped straight to the else block. So it executed y equals y plus 1, making y equal 3. X was untouched. Final output, x equals 4, y equals 3.
Section 5. Logic in action with and not. Let's combine multiple operators for a slightly tougher challenge.
Notice how the expression has grown more complex here. We're utilizing both an and comparative and a not modifier. It's asking, if x equals y, and not x is less than y.
Lean in for this one. What is the output for this specific input scenario when x is 1 and y is 1? Let's trace it out rhythmically. 1 equals 1? Yes, that's true. 1 is less than 1? That's false. But we have that not flipper attached, so false becomes true. Finally, true and true, that evaluates to true.
And this brilliantly illustrates how it works in practice. Because the overall statement is true, the program takes that first path, adding 1 to x. That leaves us with x equals 2 and y equals 1.
Let's examine one more row real quick. X equals 4, y equals 6. Remember the strictness of and? Since 4 equaling 6 is immediately false, the computer doesn't even need to work out the rest. It instantly skips to the else block, making y equal 7. X stays 4.
So, as we wrap up, it really is amazing that all the complex routing in these examples literally boils down to those 3 fundamental truth tables we learned at the start: and, or, not.
It's an incredible testament to how beautifully simple the core of computing really is, which leaves us with a fascinating thought. If vast software systems rely entirely on these atomic, absolute truths and falsehoods, how insanely complex can the questions we ask them become when we stack millions of them together?